Welcome to Shri Learning Academy. Let's simplify CPU scheduling. A quick note before we start. If you've been following our complete OS course from the beginning, we've already touched on these core concepts in previous modules, so feel free to skip ahead to the next video. However, if you're new to the channel or just need a clear, beginner-friendly refresher on the brain behind multitasking, this is the perfect place to start. Imagine this: you open your laptop, start a video, download a file, and maybe keep a browser running with 10 tabs, and somehow everything just works. Nothing fights, nothing crashes instantly, and everything feels smooth. But behind this smooth experience, there's a silent decision maker constantly asking one question: who gets the CPU next? That decision making process is what we call CPU scheduling. At its core, CPU scheduling is about managing time, not clock time, but CPU time. We already know that a process is a program in execution and multiple processes can exist at the same time. But here's the catch: the CPU can execute only one process at a time, at least in a single core system. So the operating system has to decide which process gets to use the CPU, when, and for how long. Think of it like a single cashier at a busy store. There are many customers waiting in line, each with different needs. Some just want to buy one item, some have a full cut, and some might even leave if they wait too long. The cashier cannot serve everyone at once. So someone has to decide the order. That someone in an operating system is the CPU scheduler. Now, this idea is not completely new. Earlier, when we talked about process management, we said the OS switches between processes very quickly to create the illusion of multitasking. This switching is not random, it is controlled by scheduling. To understand this better, imagine you have three processes: a music player, a browser, and a file download. If the CPU only runs one process until it finishes, the other two will just wait. That would make your system feel slow and unresponsive. Instead, the OS gives a small slice of time to each process, then switches to another and keeps repeating the cycle. This is how multiple tasks appear to run simultaneously. Now, where do these processes wait before getting CPU time? They wait in something called a ready state. You might remember from earlier discussions that processes move through different states like ready, running, and waiting. CPU scheduling mainly deals with processes that are ready to run but are waiting for their turn. So the OS maintains a list of these ready processes, often called the ready queue. The scheduler picks one process from this queue and assigns it to the CPU. But here's where things get interesting. How does the scheduler decide which process to pick? That depends on the scheduling strategy or policy, which we will explore in upcoming topics. For now, just understand that different systems use different rules depending on their goals. For example, in a simple system, the OS might just pick the process that arrives first. That sounds fair, right? But what if the first process is very long and the others are very short? The short ones will keep waiting unnecessarily. So fairness alone is not enough. Efficiency also matters. Let's take a real life example. Suppose you're at a hospital. There are patients waiting. One patient has a minor issue, another has a serious emergency. If the doctor treats patients strictly in arrival order, the emergency case might suffer. So instead, hospitals prioritize based on urgency. Similarly, CPU scheduling sometimes considers priority, execution time, or responsiveness. Another important thing to understand is that CPU scheduling works closely with something we already studied: context switching. When the CPU switches from one process to another, the OS saves the current state of the running process and loads the state of the next one. This switching happens very fast, but it still takes time. So, scheduling is not just about fairness, but also about minimizing unnecessary switches. Now let's look at two broad ways scheduling can happen. Sometimes, once a process gets the CPU, it keeps it until it finishes or goes into waiting. In other cases, the OS can interrupt a running process and give the CPU to another one. These two approaches are called non-preemptive and preemptive scheduling. We'll go deeper into this later, but for now, Just keep in mind that preemptive scheduling allows better responsiveness, especially in modern systems. Think of a classroom. In a non-preemptive setup, one student speaks until they are completely done. In a preemptive setup, the teacher might interrupt and give someone else a chance to speak. Both have their advantages depending on the situation. Now, why is CPU scheduling so important? Because it directly affects system performance. If scheduling is poorly designed, processes may wait too long, the CPU may sit idle, or some processes may never get a chance to run. On the other hand, a good scheduling strategy improves system responsiveness, ensures fairness, and makes efficient use of resources. Let's take another example. Suppose you click on an app and it takes 10 seconds to respond because the CPU is busy with background tasks. That would be frustrating. A good scheduler ensures that interactive tasks like user inputs get quick attention even if background processes are running. This brings us to an important idea. Not all processes are equal. Some are interactive, like typing or clicking. Some are background tasks, like updates or data processing. CPU scheduling often tries to balance these different needs. Also, remember that scheduling decisions happen very frequently. The OS constantly monitors the system and makes decisions in milliseconds. This is not a one time decision, but a continuous process. As we move forward, we'll break this topic into smaller parts. We'll look at different criteria used to measure scheduling performance, like waiting time and response time. We'll explore different types of queues where processes wait. And then we'll dive into specific algorithms like first come, first serve, shortest job first, round robin, and more. For now, just hold on to this core idea. CPU scheduling is the brain behind multitasking. It decides how CPU time is shared among processes. It ensures that your system feels fast, responsive, and fair even when multiple tasks are running together. That is it for this video. See you in the next one.